In this video, we're going to look at some one-step synthesis examples from the reactions that we learned in Chapter 8. So to come up with a synthesis procedure, we need to compare the reactants and the products, see what changes there are between the two compounds, and then that will lead us to what reagents we need to use to affect those changes. So far, we've really learned three different types of reactions. We've learned addition reactions in Chapter 8, and then Chapter 7, we learned about substitution and elimination reactions. And so we have all of these tools at our disposal for achieving these syntheses. So when we're analyzing these addition reactions, we want to consider three things. We want to look at what groups were added to the carbon-carbon double bond, right? And so what reagents would give rise to those two groups? We need to consider the regioselectivity. So did we add those groups via markovnikov or anti-markovnikov addition? And then if there are any stereochemical requirements, then we need to consider that. And that's primarily going to boil down to, did we add those groups syn or anti? Okay, here's our first example. So the first thing we want to ask, to go from the reactants to the products, right, what groups did we add to the carbon-carbon double bond? And so in this case, we added a water. So we put an OH here and a hydrogen here. And then, so we've got an OH and an H. And for the regioselectivity, we put the OH on the more substituted carbon. So we followed Markovnikov addition. And then we didn't create any chiral centers, and so the stereospecificity is not applicable in this case. So we need to think about what reagents will add an OH and an H, and will they do it by Markovnikov addition? And so I think we have two options. We have acid-catalyzed hydrolysis, or we have oxymercuration demercuration. Now, because in the intermediate we're going to form a tertiary carbocation, we don't have to worry about carbocation rearrangement, and so I think the easiest way to go would be with the acid-catalyzed hydrolysis. And so we could just put H3O+, but it's maybe better to be a little bit more specific, and the acid we often use for acid-catalyzed hydrolysis is sulfuric acid. And it's a catalyst, so sometimes we put catalysts in brackets. And then, if you remember, when we talked about the equilibrium between addition and elimination for adding water, we want to use dilute acid for eliminations because concentrated acids favor the elimination product. That would favor the reactants. And so oftentimes what we do is we put H2SO4 and then water, or other times we might write, we're going to use H2SO4, but we're going to do it dilute. Okay, here's our second example. And I'll be honest, when I first looked at this example problem, I was like, what the heck? Like, we didn't add anything to the carbon-carbon double bond. We turned the carbon-carbon double bond into a carbon-oxygen double bond. And then I realized, oh, this is oxidative cleavage, right? What we're doing is we're breaking these bonds. Remember, there's a CH2 here, right? And then we're putting a double bond O on both carbons that are part of the carbon-carbon double bond. So the other product that they're not showing us is formaldehyde, right? That's from this guy coming off. All right, so we're not really adding groups to the carbon-carbon double bond, but we're using ozone to do the oxidative cleavage. And then the regioselectivity isn't really relevant. Both carbons got the double bond oxygen, and it's not stereospecific. This carbon's sp2, so it's not chiral. So, these last two really aren't relevant. So we just need to remember the reagents that we use for ozonolysis to achieve oxidative cleavage. And so that is going to be ozone. And then we need the mild reducing agent. And so we can use DMS for that. Or we can use zinc and water. Okay, here's another example. Same substrate, different product. In this case, we're adding an OH here and a hydrogen here. So we're adding H and OH. This one is regioselective, right? Normally, the OH would like to go to the more substituted carbon for Markovnikov addition. So in this case, we have the OH going to the less substituted carbon. So we have anti-Markovnikov. And then we didn't make any chiral centers, so the stereospecificity is not relevant to this problem. And so to achieve anti-Markovnikov addition of H and OH, this is the hydroboration oxidation. And so the reagents for that are BH3 in THF. And then for the oxidation, we use hydrogen peroxide and sodium hydroxide. Okay, here's our final example. And so in this case, when I compare the reactants and products, I'm adding 2 OHs. So this is dihydroxylation. Right? The regiochemistry is not really relevant because they're both getting the same group. But now the stereospecificity is important, right? And so they both win on wedges. And so this is going to be syn addition. So I need to remember the reagents that I can use to get dihydroxylation with syn addition. And so that's where we can either use the osmium compound or the potassium permanganate. And so I'll use OSO4. And then we can use a co-oxidant to use a catalytic amount of the osmium compound. And so one of our choices there is NMO.